Welcome to today's problem walkthrough. In this session, we'll tackle LeetCode problem number 389, titled Find the Difference. This problem challenges us to identify the extra character added to one string when compared to another. It's a great way to sharpen your skills with string manipulation and improve your algorithmic thinking. Let's dive in. The problem we are tackling is called Find the Difference. Here, you are given two strings, s and t. The string t is created by randomly shuffling the characters of s and then adding one extra character at a random position. Your task is to figure out what that extra character is and return it. The input consists of two strings. S is a string of lowercase English letters with a length of n, while t is also a string of lowercase English letters but has a length of n plus 1. The output is a single lowercase English letter, representing the extra character that was added to t. For example, if s is ABCD and t is ABCDE, you need to determine that the extra character is e. In this example, the output is e. The explanation is that t is generated by shuffling the string s, which is ABCD, and appending one additional character, e. Therefore, the extra character is e. Now, let's consider another example where s is an empty string, and t contains just one character, y. Since s has no characters, the only character in t, which is y, must be the extra character. Thus, the output in this case is y. We can look at one more example to further solidify our understanding. Here, the input strings are s equal to ab and t equal to aabc. The string t, which is abc, is a shuffled version of s, which is ab, with one additional character, c, added. The extra character in this case is c, and that is the value we would return. This demonstrates how the problem works even when the strings contain repeated characters. To summarize the constraints of the problem, both s and t consist solely of lowercase English letters. The length of s can range from 0 to 10,000, and the strings t and s differ by exactly one additional character in t. There are a few edge cases to keep in mind. If s is an empty string, then t will contain exactly one character, which should be returned as the solution. If all characters in s are identical, ensure you can still identify the extra character in t. For example, if s is AAA and t is AAA, the extra character is the fourth out. Lastly, the solution must handle large input sizes efficiently, particularly when the length of s approaches the upper limit of 10,000. To solve the problem of finding the extra character in string t that is not in string s, we can first consider a brute force approach. The intuition here is straightforward. Iterate through each character in string t and check whether it exists in string s, along with its frequency. To implement this, we start by creating a frequency map for all characters in string s. As we traverse through string t, we decrement the frequency of each character in the map. If a character's count becomes negative or it doesn't exist in the map, we know that's the extra character, and we return it. This method has a time complexity of O, n plus m, where n is the length of s and m is the length of t. However, it does require extra space to maintain the frequency map, and updating the map introduces additional overhead, making it less efficient for larger inputs. Another approach to consider is the sorting method. The idea here is to sort both strings, s and t, and then compare them character by character. Since t contains all characters of s plus 1 extra, the first mismatch between the two sorted strings will reveal the extra character. If no mismatch is found during the comparison, the extra character must be the last one in t. While this approach is effective, its time complexity is O, n log n, because of the sorting step, which is the dominant factor. Additionally, while sorting can be done in place to reduce space usage to O(1), it still involves a computational expense that may not be necessary given the relatively simple nature of the problem. As an alternative, we can also consider the XOR approach, which is a more efficient solution making use of bit manipulation. By XORing all characters in both strings, identical characters cancel each other out, leaving only the extra character. This approach is both time and space efficient, requiring only O, n, time and O(1) space. The XOR approach stands out for its efficiency and simplicity. It works by leveraging the mathematical properties of XOR, where XORing two identical values results in 0, and the operation is commutative and associative. This means that the order of operations doesn't matter, making it robust for any arrangement of input strings. To implement this, we initialize a variable, result, to 0. We then XOR all characters in both strings together, and the result will be the ASCII value of the extra character. This solution achieves a time complexity of O(n), as we process each character exactly once, and a space complexity of O(1), since no additional data structures are required beyond a single variable. While this method is elegant and efficient, it does require an understanding of XOR, which might not be immediately intuitive to all learners. However, for scenarios like this one, where input constraints involve ASCII characters, XOR excels as a minimalistic and highly effective solution. There are some key observations that make the XOR approach particularly appealing. Its cancellation property ensures that identical characters are eliminated regardless of their order in the input, making it highly robust even when the strings are shuffled. Additionally, the simplicity of implementation, processing each character with a single XOR operation, makes it faster and more resource efficient than other methods. When comparing trade-offs, the brute force approach, while simple, is less efficient due to the need for a hash map. Sorting, on the other hand, guarantees correctness but incurs a computational cost that can be avoided. Ultimately, the XOR approach provides the best balance of time and space efficiency. It eliminates the need for extra memory or pre-processing steps and directly identifies the extra character with minimal computation, making it the optimal choice for this problem. In this problem, we need to find the first character in string T that is either missing from string S or appears more frequently in T than in S. Both strings consist of lowercase English letters, and we know that T contains exactly one extra character compared to S. One simple way to solve this is the brute force approach. Here, we iterate through each character in T, checking if it exists in S and whether its frequency matches. If we find a mismatch, we can immediately return that character. To do this, we loop through each character in T, count its frequency in both strings, and compare the counts. If a mismatch is detected, we return the extra character right away. Once we identify the first character in T whose frequency exceeds its counterpart in S, we can return that character immediately. This ensures that we stop the process as soon as the extra character is found. If, for some reason, no such mismatch is found, which is theoretically impossible due to the problem constraints, we can safely return the last character of T, as it is guaranteed to be the extra one. To optimize the brute force approach, we can use hash maps to count the character frequencies in both strings. By storing these frequencies in hash maps, we can compare them more efficiently and find the mismatch much faster. First, we initialize two hash maps to track the frequency of each character in S and T. Then, we traverse both strings to populate these maps. After the frequency maps are populated, we compare the counts for each character in the hash map of T. If we find a character whose frequency in T exceeds its frequency in S, we return that character as the extra one. This approach is efficient, as the traversal and hash map operations are linear in time complexity. Additionally, since the problem guarantees that T contains exactly one extra character, we are assured of finding the mismatch. Another optimized approach involves using the XOR operation. XOR is a clever and space-efficient method to identify the extra character. When two identical characters are XORed, the result is 0, and because XOR is commutative, the order of operations doesn't matter. This means all matching characters in S and T cancel out, leaving only the extra character. To use the XOR approach, we start by initializing a variable called result to 0. Then, we XOR all the characters in both S and T with this variable. As we process the characters, all matching pairs between S and T cancel out, leaving only the extra character from T. Finally, we convert the resulting value back to its corresponding character and return it. This method works because of the fundamental properties of XOR. Any value XORed with itself becomes 0, and any value XORed with 0 remains unchanged. In terms of complexity, the brute force method requires O(n) squared time due to repeated frequency checks, while the hash map and XOR approaches take O(n) time as both involve a single traversal of the strings. Space complexity is O(1) for brute force and XOR but O(n) for the hash map approach. This makes XOR the most efficient in terms of both time and space. Now, let's consider some edge cases to ensure our algorithm handles all scenarios correctly. For example, if all characters in S and T are identical except for one additional character in T, such as S equals AAA and T equals AAA, the algorithm should correctly identify the extra. For single character strings, where s is empty and t has one character, like s equals and t equals x, the extra character must be the only character in t. Another case is when the characters in s and t are in random order, such as s equals abc and t equals cabt. The order does not affect the correctness of the algorithm, as it relies on counts or XOR, both of which are independent of position. These examples show the robustness of the algorithm in handling a variety of inputs. This implementation leverages the properties of the XOR operation to efficiently find the extra character in string t. The find the difference function takes two input strings, s and t. The key observation is that XORing a character with itself cancels it out, e.g., a equals 0. Thus, by XORing all characters of both strings, the result will be the ASCII value of the extra character in t, as it cannot be cancelled out. First, we initialize a variable XOR_result to 0. This acts as an accumulator to store the XOR of all characters from both strings. We then iterate through each character in string s, convert the character to its ASCII value using ORed, and XOR it with XOR_result. Next, we do the same for all characters in string t. Since string t contains one additional character compared to s, this extra character will remain in XOR_result after all XOR operations. Finally, we convert the resulting ASCII value in XOR_result back to a character using CHR, and return it. This solution is efficient, with a time complexity of O(n), where n is the length of the longer string, t, and a space complexity of O(1), as no extra data structures are used. This is the Java implementation of the find the difference problem. The logic mirrors the Python solution, leveraging the XOR operation to identify the extra character in string t. Key differences include explicit type declarations and the use of Java's char and int types. The solution is efficient with O(n) time complexity, where n is the length of the longer string. To solve this problem, we start by initializing a variable called XOR_result and setting it to 0. This variable will help us track the cumulative XOR of the ASCII values of the characters in both strings s and t. Next, we iterate through each character in string s. For each character, we calculate its ASCII value using the ORed function and XOR it with the current value of XOR_result. This operation effectively combines the bits of the current character with the cumulative result, flipping them when they differ. For example, XORing the ASCII value of A gives us 97, while XORing B updates it to 3, and so on. By the end of this step, XOR_result represents the cumulative XOR of all characters in S. Now, we move on to processing the string t. Here, we continue the XOR process by iterating over each character in t and combining its ASCII value with the current XOR_result. For instance, XORing A updates XOR_result to 101, and this process continues for each character in t. The key difference is that t contains one extra character compared to s. Therefore, once we've XORed all the characters, the cumulative result, XOR_result, will isolate the ASCII value of this extra character. In this example, the final value of XOR_result is 101, which corresponds to the ASCII value of E. Converting this back to a character using CHR, 101, gives us our result, E. Let's look at another example where S is an empty string, and T contains a single character, Y. As before, we initialize XOR_result to 0. Since S is empty, there are no characters to process in the first step. We then move directly to the string T and XOR its sole character, Y, with XOR_result. The ASCII value of Y is 121, and XORing it with 0 simply results in 121. This means the final value of XOR_result is 121. Converting this back to a character using CHR, 121, gives us our result, Y. This example highlights how the XOR operation effortlessly isolates the character when only one string contains it. In this example, the strings are S equals AB and T equals ABC. As before, we initialize XOR_result to 0. Starting with the string S, we XOR each character one by one. XORing it twice cancels out its contribution because the XOR operation is self-inverse, meaning a character XORed with itself results in 0. Similarly, XORing B twice also reduces its contribution to 0. By the end of this step, XOR underscore result is 0 because all characters in S have been paired and cancelled out. Next, we process the string T. Here, the characters at NB appear twice and cancel out, just as they did in S. However, the character C appears only once in T, so its ASCII value, 99, is added to the cumulative XOR result. At this point, XOR underscore result holds the value 99. Finally, with O XOR underscore result value of 99, we know this corresponds to the ASCII value of the extra character in T. Using the CHR function, we convert 99 back to the character C. This character is the one that is present in T but not in S, which makes it our result. By returning C, we successfully solved the problem for this input. This approach demonstrates how the XOR operation effectively isolates the differing character by leveraging its properties of cancellation and self-inversion. In this solution, we use the XOR operation to efficiently find the extra character in string T. To analyze the time complexity, consider that the length of string S is n, and the length of string T is n plus 1 because it includes the additional character. First, we perform XOR operations on all the characters in S. This involves a loop iterating over each of the n characters, where for each iteration, we retrieve the ASCII value of the character using the ORD function and apply the XOR operation. Both of these steps, retrieving the ASCII value and performing XOR, happen in constant time, or O(1), per character. Since the loop runs n times, this part of the algorithm contributes O(n) to the total time complexity. Next, we process string T in a similar manner. Here, the loop iterates over all n plus 1 characters, and like before, each operation within the loop is O(1). Therefore, this part contributes O(n plus 1) to the total time complexity. Finally, after both loops, we convert the cumulative XOR result into a character using the CHR function. This operation is also constant time, or O(1). When we sum up the contributions from these steps, the total time complexity becomes O(n) from the first loop, O(n plus 1) from the second loop, and O(1) from the final conversion. Combining these, we get O(2n plus 2). Since we drop constants in big O notation, this simplifies to O(n), meaning the algorithm scales linearly with the size of the input. Now, let's analyze the space complexity. This solution relies on the XOR operation to find the extra character, which requires only a constant amount of additional memory. Specifically, the variable XOR underscore result is used to store the cumulative XOR value, and this single integer variable occupies O(1) space. The input strings S and T are part of the problem's input and do not count as additional space, as we're not creating new data structures. Similarly, the output, which is a single character, also uses constant space. Therefore, the auxiliary space required by this algorithm is minimal. When we consider the total space complexity, the absence of data structures or recursive calls dependent on the input size means the algorithm's space usage remains constant at O(1). To understand why this approach is advantageous, let's compare it with some alternative methods. A sorting-based approach, for example, would require sorting both S and T, which has a time complexity of O(n log n). Comparing characters after sorting would add an additional O(n). On the space side, sorting can require additional memory, especially if the implementation is not in place, leading to a potential O(n) space complexity. Another common approach is frequency counting, where we use a hash map or an array to store character counts. While this can achieve O(n) time complexity for iteration, the space complexity depends on the implementation. A fixed-size array for ASCII characters would use O(1) space, but a hash map could require OK, where K is the number of unique characters. Both of these methods, while valid, introduce overhead in terms of either time or space. The XOR-based solution avoids these inefficiencies, making it optimal in both time and space. With a time complexity of O(n), it matches the performance of the frequency counting approach but eliminates the need for additional data structures. Its space complexity of O(1) is the best possible, as it only uses a single variable for computation. The efficiency of the XOR approach lies in its mathematical properties. XOR has the unique characteristics that A equals 0 and A0 equals A. By XORing all characters in S and T, the matching characters cancel each other out due to the A equals 0 property, leaving only the extra character in T. This elegant mechanism eliminates the need for sorting, frequency counting, or other complex operations, making the XOR approach highly efficient and straightforward for this problem. When approaching this problem, there are some common mistakes to be mindful of. First, misinterpreting the problem is a frequent issue. It's important to understand that we're not just finding missing characters but specifically identifying the extra character in the second string, T. For example, if T has characters that aren't in S, those must be accounted for correctly. Misunderstanding this can lead to incomplete or incorrect solutions, particularly in edge cases. Speaking of edge cases, ignoring scenarios where S or T is empty, or where T includes duplicate characters not in S, is another pitfall. For instance, if S is ABC and T is ABCD, the solution should correctly identify D as the extra character. Beyond logic errors, inefficient strategies like using nested loops to compare character frequencies can result in quadratic time complexity, which is too slow for large inputs. Similarly, sorting both strings and comparing them might seem intuitive but introduces an unnecessary O, n log n, cost, making it less optimal than linear approaches. Being aware of these trade-offs and pitfalls is critical to crafting a robust solution. Another common issue arises when candidates fail to handle uppercase and lowercase letters correctly. If the problem specifies case sensitivity, confusing it with it can lead to incorrect results. This is especially important in scenarios involving ASCII values or specific mappings. Now, when it comes to standing out in an interview, several key practices can help. Recognizing patterns is essential, as many string problems revolve around character frequency analysis. Using a hash map or an array to track frequencies is a common and efficient approach. Interviewers also look for optimal time complexity, so aim for O(n) solutions by leveraging tools like hash maps or XOR operations, rather than relying on slower methods like sorting. Additionally, always communicate edge cases clearly during your explanation. For instance, consider what happens if T is longer than expected or if the strings contain non-alphabetic characters. Finally, be prepared to discuss trade-offs between approaches. Sorting is straightforward but slower, XOR is elegant but less readable, and hash maps strike the best balance between clarity and efficiency for most scenarios. This problem is closely related to other string manipulation challenges that also involve analyzing character frequencies. For example, LeetCode 242, valid anagram, is about checking if two strings are anagrams using frequency counts, which is conceptually similar. LeetCode 383, ransom note, requires verifying if one string can be constructed from another, again relying on frequency analysis. Another related problem is LeetCode 266, palindrome permutation, which involves determining if a permutation of a string can form a palindrome based on its character frequencies. Finally, LeetCode 49, group anagrams, focuses on grouping strings with identical characters, which can be solved using either sorting or hashing techniques. Exploring these problems can deepen your understanding of frequency-based approaches and help you recognize patterns that frequently appear in string manipulation challenges. When solving this problem, there are several approaches to consider, each with its own trade-offs. Using a hash map to count character frequencies in both S and T is one of the most efficient methods. It runs in O(n) time and is easy to understand, though it does require extra space for the hash map. Another option is sorting both strings and comparing them character by character. While simpler to implement, this approach is slower, with a time complexity of O(n) log n, due to the sorting step. Alternatively, you can use XOR to find the differing character in O(n) time with O(1) space. This method is elegant and highly efficient but can be less intuitive for some, so it's important to explain how XOR works during an interview. The key insight here is that most string problems involving mismatched characters can often be reduced to frequency analysis. Hash maps typically provide the best balance of clarity and efficiency, making them a reliable choice in interview settings. Great job following along. To wrap up, we reviewed the problem, summarized the approach, and highlighted the key takeaways. Remember, mastering these concepts takes practice, and you're making great progress. Thanks for watching, and be sure to check out more sessions for additional practice. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!